and millions of transit passengers. Just look at Dubai. It is an absolute giant. You see endless rows of the Airbus A380s and terminals packed with people. It is impressive, sure, but let's be honest, it is also chaotic and stressful. Now look at this. This is Muscat. It is calm. It is beautiful. Just a modern Boeing 787 waiting at the gate. While its neighbors are still fighting to be the biggest superconnector, Oman Air has decided to stop the race. They said enough. Instead of copying the giant, they are building the anti-Emirates. Today we are going to look at why Oman Air is shrinking its fleet and why becoming smaller might be the smartest move in aviation in 2026. But first, hit the like and subscribe button. This simple action is vital for me. Thank you very much. The superconnector trap. To understand Oman Air's new plan, we first need to look at the giants next door. For a long time, the aviation world in the Middle East was defined by Emirates, Qatar Airways and Etihad. Their model is legendary. Build a massive airport in the desert, buy hundreds of wide-body planes and connect the entire world through one single hub. It works perfectly for Dubai and Doha, but for everyone else, it is a dangerous trap. Just look at Etihad Airways in Abu Dhabi. A few years ago, they tried to grow too fast. They wanted to catch up with Emirates at any cost. The result was a disaster. They lost billions of dollars and almost went bankrupt. Oman Air was heading down the exact same path. For years, they tried to be a major transit hub. They wanted to funnel millions of passengers through Muscat, just like their neighbors. But the math didn't work. The airline was losing money consistently. They were burning cash just to keep up with the competition. Finally, the leadership realized a hard truth. The market is full. To survive, Oman Air didn't need to get bigger. They need to stop copying the giants and find their own way. The boutique philosophy. So what is the solution? Oman Air calls it the boutique airline strategy. The goal was simple. Get passengers to fly through Muscat to reach London, Bangkok or Sydney. Oman was just a transfer point. But that era is over. Now the focus has shifted from transit to destination. They want to bring tourists to Oman, not just move them across the map. This means they are no longer chasing numbers. They don't want to carry millions of passengers who are just looking for the cheapest economy ticket. Instead, they are focusing on quality. They want the premium traveler who values comfort over house. Think of it like the hotel industry. Emirates is like a massive 5-star mega resort with 3,000 rooms. It is impressive, but it is crowded and you are just one of thousands of guests. Oman Air wants to be the exclusive boutique hotel with only 50 rooms. It is quiet, personal and curated. They are proving that you don't need to be the biggest to be the best. One world, the secret weapon. So how do you survive as a small airline surrounded by sharks? The answer is simple. You don't fight alone. This is the biggest difference between Oman Air and Emirates. Emirates is famous for doing everything by itself. They don't join alliances. They rely only on their own fleet. But Oman Air knows it cannot win that way. In 2025, they made a game-changing move. They officially joined to the One World Alliance. This is their secret weapon. Suddenly, Oman Air doesn't need to buy hundreds of planes to reach the world. By joining the alliance, they instantly gained access to over 1,000 destinations. They can now sell you a ticket to almost anywhere on the planet, using their partners' networks. For years, Qatar was the fierce rival next door. But now, because they are both in one world, the former enemies are partners. Instead of fighting a price war for every single passenger, they can now cooperate. It is a brilliant strategy. Stop the expensive war and start sharing the profits. Optimization over scale. To make this new strategy work, Oman Air had to make some tough choices about their hardware. First, they decided to kill the Airbus A330 fleet. These planes served them well, but they are older and less efficient. In the new boutique era, every drop of fuel counts. Instead, they are betting everything on the Boeing 787 Dreamliner. This is the perfect tool for their mission. Unlike the massive A380, which needs 500 passengers just to break even, the Dreamliner is smaller and lighter. It allows Oman Air to fly long distances on thin routes. Routes that are profitable but simply does not have enough people to fill a giant double-decker plane. For shorter flights, especially to connect with India and neighboring countries, they rely on the 737 MAX. It is efficient and does the job perfectly. But the biggest change is inside the cabin. You won't find first class on their new planes. Oman Air realized that flying empty first-class suites is a waste of money. Instead, they introduced the Business Studio. This is a super business class. It offers the privacy and luxury of first class, but at a price point that makes sense. It is smart luxury, not wasteful luxury. The airport experience. If you have ever transferred through Dubai, you know the struggle. You land, you wait for a train between terminals, you walk for 20 minutes, and you stand in endless lines. It is loud, crowded, and stressful. Honestly, it often feels more like a giant shopping mall than an airport. Muscat offers the complete opposite. It is a definition of stress-free. The new terminal in Muscat is designed for speed and comfort. Everything is under one roof. You can walk from your arrival gate to your departure gate in just a few minutes. There are no trains to catch and no marathon walks to endure. The design reflects the country itself. While Dubai screams busy and expensive, Muscat is calm and welcoming. It uses natural light, quiet spaces, and elegant architecture. It turns the worst part of travel, the layover, into a moment of relaxation. For a passenger tired after a long flight, silence is the ultimate luxury. The anti-Dubai destination. An airline is always a mirror of its country. Just as Oman Air is the opposite of the Emirates, the country of Oman is the opposite of Dubai. Dubai is famous of having the tallest skyscrapers, artificial islands, and endless hype. It is impressive, but it often feels man-made. Oman is completely different. It is the anti-Dubai. Here, instead of glass towers, you see jagged mountains. Instead of giant shopping malls, you see ancient forts and traditional markets. It offers an authentic Arabian experience, not a theme park. Oman Air uses this difference to its advantage. They don't just want you to change planes, they want you to step outside. That is why they heavily promote their stopover program. They allow passengers to stay in the country for a few days at no extra flight cost. It is a clever deal. Why spend your layover sleeping in an airport chair when you could be exploring the mountains? So will this bold strategy actually work? It is definitely a risk. In the business world, we are usually taught that growth is good. Shrinking your airline to make more money sounds a bit crazy. However, Oman Air is betting that quality wins over quantity. By flying fewer planes and focusing on higher-paying passengers, they hope to finally become profitable after years of losses. In a world where flying often feels like taking a crowded bus with wings, Oman Air is trying to bring back a sense of exclusivity. They realized they cannot beat Emirates at their own game, so they simply stopped playing it. They do not want to be the biggest airline on the planet. They just want to be the best airline for their niche. Now I want to ask you, what would you choose for your next trip? A quick, quiet transfer in Muscat or the shopping and bright lights of Dubai? Let me know in the comments below. If you learned something new today, hitting the subscribe button is the best way to support me. As a new channel, every subscriber truly counts and motivates me to create better stories. Click here to watch the next video. Thanks for watching and see you next time. Imagine an aircraft that literally every major airline in the world was begging to buy. A plane so perfectly designed that it could revolutionize how we fly,
cutting ticket prices, unlocking hundreds of new direct routes, and completely changing the economics of the airline industry. It was the absolute perfect machine. Sounds amazing, right? Well, there's just one massive problem. It doesn't exist. And honestly, it probably never will. Today we're talking about the ultimate ghost of the aviation industry, a plane that has been obsessed over boardrooms and aviation forums for nearly a decade. The Boeing 797. Was it really the perfect aircraft? And if it was so perfect, why can't you buy a ticket on one today? Before we dive into the secret engineering, make sure you hit that like button and subscribe to the channel. It takes just a second, but it really helps push these aviation deep dives out to more people. Alright, let's get into it. To understand why the 797 was considered perfect, we first have to understand the massive headache that airlines have been dealing with for the last 15 years. In the aviation world, there is a legendary dead zone called the middle of the market, or the MOM. For decades, this gap was filled by two legendary Boeing aircraft, the 757 and the 767. The 757 was this incredibly overpowered, long, single-aisle rocket ship that could take off from short runways and cross the Atlantic. The 767 was a small, twin-aisle widebody that dominated transcontinental and medium-aisle international flights. But here's the issue. Those planes were designed in the late 70s and 80s. They are aging, they are gas guzzlers by modern standards, and airlines have been retiring them. So airlines desperately needed a replacement. They needed a plane that was bigger and has longer legs than a standard narrow body like a 737 or an A320, but wasn't a massive, heavy and expensive to operate as a widebody like a 787 Dreamliner or an A350. They needed a Goldilocks plane. Not too big, not too small, just right. Enter the 797. Now, just to be precise with the facts here, Boeing never officially called it the 797. Inside the company, this was known as the NMA, the new mid-size airplane. The proposed specs for the NMA were exactly what airlines were dreaming of. The NMA 6X, which would carry about 225 passengers and fly roughly 5,000 nautical miles, and the NMA-7X, a slightly larger version carrying 275 passengers with a range of 4,500 nautical miles. The economics were supposed to be mind-blowing. Boeing targeted a 40% lower trip cost compared to the older widebodies it was replacing, while generating 30% more revenue than existing narrow bodies. It was perfectly designed for long but thin routes. Think about flights from St. Louis to London, or Chicago to secondary cities in Europe, or pushing deep into South America from the US. Routes where you simply can't fill a 300-seat widebody, but you still need the range to cross an ocean. Over 50 airlines, huge players like Delta, United and Qantas, were practically throwing their wallets at Boeing, begging them to build this thing. Qantas even publicly stated they wanted to be their launch customer. But as Boeing dug into the actual engineering, the perfect plane started to reveal some nearly impossible design paradoxes. And this is where the story gets really interesting. Most people just assume the 797 would be a shrunken down 787 Dreamliner, a carbon fiber tube with some new engines. For example, as the 787-3. Have you ever heard of it? By the way, I've created a video about it and it will appear somewhere here. But that wasn't the case at all. Behind closed doors, Boeing realized that a standard widebody design wouldn't work for the economics they needed. Airlines insisted on the 797 being a twin-aisle aircraft. Why? Because twin aisles mean faster boarding and deplaning times. If you have 250 people cramming onto a single-aisle plane, the turnaround time at the gate is brutal. And airplanes only make money when they are in the air. A 2-3-2 seating layout with two aisles solves that. But there is a catch. Twin-aisle jets typically have massive circular fuselages, which creates a massive cargo holds underneath the passenger floor. Airlines aren't moving that much cargo, they are moving people. So huge circular fuselage just creates unnecessary weight and drag, killing the fuel efficiency. They decided to design an entirely new ovoid or elliptical fuselage. Imagine a shape that is wide at the top to accommodate the two aisles, and the passengers but narrow at the bottom, like a single aisle jet, to reduce drag and minimize the empty cargo space. It looks brilliant on a blueprint, but in reality, physics hates an oval. When you pressurize an aircraft cabin at 35,000 feet, a perfect circle distributes the stress evenly. An oval creates massive stress concentrations at the curves. Building a pressurized ovoid fuselage, especially out of carbon fiber, is incredibly difficult and notoriously heavy, because you have to reinforce the structure so much to keep it from failing. And that leads us right into the great materials debate. Everyone thought the 797 would be entirely composite, like the 787. But to make this plane perfect, it had to be cheap. Airlines are notoriously frugal, and the market consensus was that to be competitive, Boeing needed to price the 797 somewhere between $65 million and $75 million per unit. To put that into perspective, a 787-8 has a list price of well over $100 million. Building composite barrel sections is exceptionally expensive. To save even more billions in research and development, the 797 was starting to look like a bit of a Frankenstein aircraft. Early renderings and insider leaks showed it would borrow heavily from Boeing's greatest hits. It was slated to feature the massive dreamable cabin windows of the 787, but the cockpit windscreen lineage was lifted straight from the old 757 and 767. The tail cone aerodynamics were derived from the 737 MAX, and the door arrangements mimicked the 767-200. It was a parts bin plane wrapped in a highly experimental oval fuselage. But even if Boeing figured out the shape and the materials, they ran headfirst into the wall they couldn't control: the engines. To make the crazy economics of the 797 work, Boeing needed a revolutionary engine. They needed something in the 45 to 50,000 pounds of thrust class that was 20 to 30% more fuel efficient than current technology. And the brutal truth, nobody had one. Rolls-Royce, General Electric and Pratt & Whitney simply didn't have an engine ready for Boeing's original target launch date of the 2025. Rolls-Royce even formally pulled out the competition for the NMA in 2019, stating their ultra-fun technology just wouldn't be mature enough in time. So, you have incredibly complex, potentially expensive fuselage, missing the engines required to make it fly efficiently, but even then, they might have spent the billions required to make it happen. But then, 2019 happened. The 737 MAX crisis fundamentally alerted the trajectory of the Boeing company. Following the tragic crashes and the subsequent grounding of the entire MAX fleet, Boeing had to pivot absolutely every ounce of its engineering talent, its financial resources, and its regulatory focus toward fixing and recertifying the 737 MAX. The company was bleeding billions of dollars. They simply did not have the capital or the bandwidth to launch a brand new clean sheet aircraft program that would cost upwards of $15 to $25 billion to develop. In January 2020, then CEO Dave Calhoun officially drove the final nail into the coffin. He publicly paused the NMA project, stating that the competitive landscape had changed and Boeing needed to start with a clean sheet of paper. When they were ready, the 797, as we knew it, was that. And while Boeing was fighting fires and posing their perfect plane, Airbus swooped in and practically stole the entire market. Airbus looked at the middle of the market gap and decided not to spend $20 billion inventing a new plane. Instead, they took their existing, highly successful A320 platform and pushed it to its absolute physical limits. The result was the A321 XLR. The XLR is a single-aisle plane. It doesn't have the fast boarding or the spacious comfort of the twin-aisle 797 concept. But you know what it does have? It has a range of 4,700 nautical miles. It carries up to 244 passengers. And most importantly, it actually exists. Airlines that grew tired of waiting for Boeing's perfect paper plane, including massively loyal Boeing customers like United and American Airlines, bought the A321 XLR by the hundreds. It's entering service right now, in the mid-2020s, exactly when the 797 was supposed to dominate. Airbus won the middle of the market without even building a new airplane. So what happens now? Will we ever see a Boeing 797? The short answer is no, not anytime soon, and certainly not as a twin-aisle ovoid mid-size plane we originally pictured. Fact-checking current statements from Boeing leadership reveals a harsh truth. Boeing will not launch a new clean-sheet aircraft until next-generation propulsion technology, like the open-fan engines, matures. And when the 2030s roll around, the threat isn't just Airbus anymore. A company called JetZero, heavily backed by the US Air Force, is currently building a blended wing-body demonstrator jet. They are targeting a 250 passenger capacity with a 5,000 nautical mile range. Those are the exact specs of the 797. But because of the radical blended wing design, they are promising up to a 50% reduction in fuel burn. By the time Boeing is ready to build their next plane, the entire concept of what a perfect aircraft looks like might have completely changed. The Boeing 797 was an aerodynamic and economic tightrope walk. It was an ambitious, beautiful concept designed for a specific moment in time. But bad timing, corporate crisis, and lack of ready engine technology, and the brutal reality of physics kept the perfect aircraft locked in the hangar forever. What do you guys think? Should the Boeing have risked it all and built the 797 anyway? Or did Airbus just play the game better with the A321 XLR? Let me know your thoughts down in the comments. If you enjoyed this deep dive into the 797, please make sure to drop a like on the video and subscribe to the channel for more aviation content. It means a lot and helps me keep making these videos. Thanks so much for watching, and I'll see you in the next one. Why Delta keeps flying the 717 against all logic? Picture this. You are walking through a major Delta hub, like Atlanta or Detroit. Everywhere you look, you see the future of aviation. You see the sleek, futuristic Airbus A350. You see the brand new, fuel-efficient A321neo. Everything feels premium, modern, and expensive. But then you look at the next gate. Sitting there is a small, strange-looking plane. It has its engines at the back, near the tail. It's loud, it's old, and it looks like a time traveler from the 90s. This is the Boeing 717. And here is the big question. Delta calls itself America's premium airline. They spend billions of dollars on new technology. So why is the backbone of their short-haul fleet a plane that competitors like Southwest sent to the scrapyard 10 years ago? You might think it is just nostalgia, or maybe a mistake. But it is not. In fact, keeping this old gas guzzler in the sky is actually one of the smartest, most calculated financial moves in modern aviation history. Let's find out why. But first, hit the like and subscribe button. This simple action is vital for me. Thank you very much. Part 1. Boeing's adopted son. First, we need to clear up a common misunderstanding. If you look at the safety card in the seat pocket, it says Boeing 717. But if we are being honest, this isn't a real Boeing plane. It was actually born as the McDonnell Douglas MD-95. It was the last great design from the legendary creators of the DC-9. But in 1997, Boeing bought McDonnell Douglas. They took the MD-95, slapped a Boeing logo on it, and renamed it the 717. But here is the sad part. Boeing didn't really want this plane. Why? Because they already had their own small plane, the 737-600. They didn't want the 717 to compete with their own baby. So Boeing killed the project very quickly. In the end, only 156 of these planes were ever built. To give you some context, there are over 11,000 Boeing 737s. The 717 is incredibly rare. And this is where it gets interesting. Delta owns or leases more than a half of all 717s left in the world. Basically, Delta is practically the only major airline keeping this rare bird alive. Part 2. The logic of free plane. So here is the big economic mystery. Everyone knows the new Airbus A220 is a masterpiece. It is modern, light, and it burns about 20% less fuel than the old 717. On paper, the A220 wins easily. But there is a trap, the price tag. A brand new A220 costs about $35 to $40 million. Even if you don't buy it, leasing one requires a massive payment every single month. Now let's look at the 717. Delta bought most of these planes almost for free. When Southwest Airlines bought AirTran, they hated the 717s and wanted them to gone immediately. Delta happily picked them up for pennies on the dollar. This changes the math completely. It comes down to capital cost versus operational cost. Think of it like a car. If you have a brand new car, you have a huge monthly payment. But if you drive an old car that is fully paid off, you don't have that monthly bill. Since your car costs you zero, you don't mind if it uses a little extra gas. That is Delta's secret. Because the 717s are fully paid off, they don't lose money when they are sitting on the ground. If a new A220 sits at the gate doing nothing, it is burning cash because of the expensive lease. But if a 717 sits at the gate, it costs Delta almost nothing. This gives them incredible flexibility. Part 3. The secret weapon. Delta Tech Ops. Usually, airlines are terrified of old planes. Why? Because maintenance is a nightmare. When a 25-year-old part breaks, it is hard to find and very expensive to replace. If you are a normal airline, this destroys your profit. But Delta is not a normal airline. They have a secret weapon called Delta Tech Ops. While other airlines have to pay third-party companies a huge amount of money to fix their engines and airframes, Delta does it in-house. They don't need to hunt for expensive rare parts. They have the skills to refurbish old parts themselves. Or they simply take what they need from donor planes that they bought just for spare parts. Because they control their repairs, keeping the 717 fleet alive costs them pennies compared to what it would cost to anyone else. Part 4. The perfect niche and the tank factor. So where does Delta actually fly these old planes? They don't fly across the ocean. They fly very short routes, often just 40 to 60 minutes. Think of a flight from Atlanta to Charlotte. In the aviation world, these are called high-cycle operations. And this is where the logic gets even stronger. You see, a modern plane like the A220 is incredibly efficient when it is cruising high in the sky. But on a 40-minute flight, the plane barely reaches cruising altitude before it has to come back down. Because of this, the new A220 doesn't have time to use its fuel-saving technology. On short hops, the fuel difference between an old 717 and the new A220 is actually very small. Also, short flights are hard on airplanes. Taking off and landing 4 or 6 times a day puts a lot of stress on the metal. It wears the plane out quickly. Why would you ruin a shiny, expensive, brand new jet on these rough, short flights? It makes no sense. The 717, however, is built like a tank. It was designed for this abuse. Plus its engines, the Rolls-Royce BR715s, they are gold standard of reliability. While modern engines are sensitive and complex, these old engines just keep working, day after day. Part 5. The Crisis of New Planes. Here's the biggest plot twist of the story. Delta actually had a plan to retire the 717 fleet. They placed a huge order to the Airbus A220, intending it to take over these routes. It seemed like a perfect plan, but there was a problem they didn't expect. The A220 used high-tech engines from Pratt & Whitney, called the GFT. While these engines are efficient, they have suffered from serious reliability issues. They require frequent inspections and often need long, complex repairs. This created a disaster for many airlines. Brand new A220s are often forced to sit on the ground waiting for engine fixes. So here is the ultimate irony. The plane that was supposed to be scrapped, the 717, is now the hero of the fleet. It is saving Delta's schedule, while the shiny modern jet are stuck in the hangar with engine problems. This old, obsolete 717 is flying every day without complaints. In the strange turn of events, the old technology turned out to be more reliable than the new. Part 6. What about the passengers? You might think that flying on an old, cheap plane means a bad experience for you. But actually, the opposite is true. Frequent flyers often love the 717 more than modern jets. First, there is the seating layout. Most narrow-body planes like the Boeing 737 or Airbus A320 have 3-to-3 setup. This means there are 2 terrible middle seats in every row. But the 717 is different. It uses a 2-3 layout. There is only 1 middle seat per row. If you are traveling as a couple and you pick the left side, you have the whole row to yourself. No strangers next to you. Second, it is surprisingly comfortable. Because the engines are located all the way at the back of the plane, the front of the cabin is incredibly quiet. It is one of the most peaceful riders in the sky. Finally, Delta didn't just leave these planes to look old. They completely updated the interiors. When you step on board, you see new seats, modern lighting, power outlets, and high-speed Wi-Fi. Most passengers sit down, connect their phones, and have no idea they are flying on a machine built in the last century. Final. The long goodbye. In the end, the Boeing 717 is much more than just an old airplane. It is a true workhorse. It allows Delta to make a profit on routes where other airplanes might lose money. It survives because it is simple, tough, and fully paid off. So when it finally leaves the skies, Delta keeps pushing the day back. Current estimates say these planes will keep flying until at least 2030. But when the last 717 finally retires, it will be a sad day for aviation enthusiasts. It will mark the end of an era, the end of the T-tail jets in major American skies. But what about you? Have you ever flown on a Delta 717? Did you notice the quiet cabin or the 2-3 seating? Or did it just feel like any other flight? Let me know in the comments below. If you learned something new today, hitting the subscribe button is the best way to support me. As a new channel, every subscriber truly counts and motivates me to create better stories. Click here to watch the next video. Thanks for watching and see you next time.
Have you ever lost your house keys? It happens to everyone. Now imagine losing something much bigger. Imagine the world losing 4 massive Boeing 777 airplanes. Each one weighs 200 tons. In December 2022, something incredible happened. Several of these jets, which used to fly for Singapore Airlines, took off from storage airports in Uzbekistan and Cambodia. They climbed into the sky and then they simply dissolved into thin air. But they didn't crash. There was no emergency. Instead, these American-made giants secretly landed in Tehran. How is this possible? How did Mahan Air, the most sanctioned airline in the world, manage to smuggle 4 modern airliners right under the nose of the CIA? Let's find out. But first, hit the like and subscribe button. This simple action is vital for me. Thank you very much. Chapter 1. The Madagascar Gambit. So, how do you legally buy a plane if the world forbids you from buying one? The answer is simple. You don't use your own name. You use a shell company. This is a fake business set up in places like UAE or Gambia. On paper, it looks like a normal company buying a plane for travel. But in reality, it is just a mask. But buying the plane is only step 1. You also need to register it. For these Boeings, the smugglers used a clever trick. They registered the planes with the code 5R, which belongs to Madagascar. Why Madagascar? Because the aviation control there is weak, and regulations are easy to bypass. They created a fake airline that claimed it would fly charter flights for tourists. It was the perfect cover. Then came the escape. The planes flight a normal flight plan, for example flying towards Uzbekistan. They took off and everything looked standard. But then, they reached a specific point in the sky, usually over Afghanistan. At this exact moment, the pilot turned off the transponder, the device that tracks the plane. The dot disappeared from the radar screens. The plane became a ghost. The pilot changed course and flew directly into Iran. This is known as the blue service method. It is the exact same trick they used to smuggle Airbus A340s before. It is risky, but it works. Chapter 2. The Technical Detectives. Why did they choose these specific planes? Why is the Boeing 777-200ER? These were not new jets. They were retired planes from Singapore Airlines and Knox Scoot. For a long time, they were just sitting in the desert, like the famous airplane graveyard in Alice Springs, gathering dust and waiting to be scrapped. Then, they were moved to Asia. But the real secret lies under the wings, the engines. These planes are powered by the Rolls-Royce Trent 800. This is the critical detail. Most modern Boeing 777s use G90 engines made by General Electric. The problem for Iran is that General Electric is an American company that watches everything. They track every screw and every sensor. It is a nightmare for smugglers to get parts for them. Rolls-Royce is British. While they are also under sanctions, the black market for their parts is slightly softer. Iran may already have old connections to get what they need. There is also a simple economic reason. Nobody else wants these planes. The Trent 800 is an older, thirsty engine. It burns a lot of fuel compared to modern jets. On the legal market, these planes are almost worthless. This makes them incredibly cheap to buy with cash. For a smuggler, they were the perfect bargain. Chapter 3. Cannibalism and donor planes. You might wonder, why did they steal 4 or 5 planes? Maintaining just one huge Boeing is already a headache under sanctions. Maintaining a whole fleet seems impossible. The strategy is dark but smart. In the aviation world, it's called cannibalism. Here's how it works. Iran buys 4 planes, but they only plan to fly 2 of them. The other 2? They are doomed. They become organ donors. When a fuel pump breaks or a computer fails on the flying plane, they don't order a new part from America. They just walk to the hangar, rip the part out of the grounded plane, and install it on the active one. It is much cheaper and more reliable than trying to find smuggled spare parts on the black market every week. But hardware is only half the battle. These planes have no access to official Boeing software updates. There are no service manuals or technical support. If a warning light turns on, you can't call customer service. This has forced Iranian technicians to adapt. Over the years, they have become masters of reverse engineering. They have learned to fix complex American technology without instructions, keeping these metal birds in the sky long after they shouldn't have been grounded. Chapter 4. Geopolitics and the powerlessness of the West. This brings up to the big question: where was the United States? The US had the most powerful military and intelligence network in the world. Why didn't they shoot these planes down or arrest the pilots? The answer is a frustrating legal dialogue. You cannot simply arrest a plane while it is flying 30,000 feet in the air, especially over neutral or friendly territory. Until the wheels touch the ground in a country that follows US laws, American authorities are powerless. They likely watched the shout happen on their screens, but they couldn't do nothing to stop it. So what is the future of the stolen giants? They cannot fly to London, Paris or Berlin. If one of these stolen 777s lands in Europe or North America, it will be seized immediately by lawyers and authorities. Instead, these planes will fly a limited network. You will see them on domestic routes inside Iran or flying to friendly hubs like Moscow, Beijing, Istanbul and maybe Dubai. They are big birds in a small cage. There is a deep irony here. These are American machines, built by American workers in Seattle. Now they are the pride of a regime that considers the US as an enemy. It is a strange reality. A country that burns American flags on the streets is desperate to fly in American planes in the sky. Conclusion: the price of risk. So Iran did it. They showed the world a masterclass of bypassing sanctions. They tricked the regulators and they got their prize. But this is a victory with a very heavy price. Ask yourself this honestly. Would you feel safe on that seat? We are talking about a plane that is being kept alive by cannibalizing other aircraft. It has not had an official technical inspection for years. It is flying without manufacturer's safety net. It is basically a Frankenstein monster of the skies. Ultimately, this story is not just about aviation enthusiasts or secret agents. It is a story about survival. It shows us exactly how far a government will go to keep its economy moving. Every rule in the book. Now I want to turn the question to you. Knowing the history of these ghost planes, knowing they are fixed with scavenged parts, would you buy a ticket? Write in the comments below. Would you risk flying on this Mahan Air 777? If you learned something new today, hitting the subscribe button is the best way to support me. As a new channel, every subscriber truly counts and motivates me to create better stories. Click here to watch the next video. Thanks for watching and see you next time.
Take a close look at this image. To most people, this looks like a pilot's worst nightmare. But to an engineer, this is a masterpiece. This is a triumph of design. On September 3, 2025, something incredible happened. In a single day, two different business jets, a Gulfstream G150 in Chicago and Challenger 300 in Boca Raton, overran the runway. Both planes were heavy, moving fast and running out of pavement. Both should have ended up in a highway or a building. But they didn't! They stopped safely, the passengers walked away, and the planes didn't even catch fire. They were saved by a technology that hides in plain sight at the end of the runway. EMAS, the Engineered Materials Arresting System. Today we are going to look at the hidden engineering that keeps you alive when a landing goes wrong. But first hit the like and subscribe button. This simple action is vital for me. Thank you very much. The science of soft concrete. So what actually is a mass? If you look at the end of a runway, it looks like a normal extension of the pavement. But it is not. It is a trap. The secret lies in the material itself. This is made of cellular cement, also known as format concrete. Imagine a block of concrete, but instead of being solid, it is filled with millions of tiny air bubbles, like a honeycomb. The engineering brilliance here is not about strength, it is about weakness. Normal concrete, the kind you walk on, is incredibly strong. It can withstand pressure of 4,000 psi, pounds per square inch. If a plane hits that, the landing gear snaps. But EMAS blocks are engineered to be weak. They have a specific crush strength of only 30 to 50 psi. Compare 4,000 to 30 or 50. This number is very precise. It is strong enough to support the weight of a fire truck or a maintenance vehicle without braking. But the moment the thin tires of a heavy jet hit the blocks, the material gives up. It crushes instantly. Part 2.
The physics of arrestment. When a plane enters the EMAS bed, the tires slice through the material like a knife through dry foam. The wheels sink into the bed. This creates drag. The material absorbs the kinetic energy of the moving aircraft and converts it into mechanical crushing work. It acts like a giant brake pad made of stone. The system is designed to stop a critical aircraft, usually a heavy jet, entering the bed at speeds up to 70 knots, about 130 km per hour. And the most important part, it does this smoothly. The bed is usually built as a ramp. It starts shallow, maybe just a few inches deep, and gets deeper towards the end, sometimes up to 30 inches. This slows the plane down progressively, so the passengers don't feel a violent impact. Part 3. The problem when space runs out. Why do we need this expensive technology? Why not just make the runway longer? The Federal Aviation Administration, FAA, has a strict rule. Every runway must have a safety net. This is called the RSA, or Runway Safety Area. The standard RSA must extend 1,000 feet, about 300 meters, beyond the end of the runway. This is a flat, empty, grassy area where a plane can roll safely if it fails to stop. But look at the map. Many airports are built 50 or 60 years ago. Since then, cities have grown around them. Some airports end at the edge of a cliff. Others end at a busy 6-lane highway. Some, like LaGuardia or San Francisco, end directly in the ocean. And these places you cannot just add land. It is physically impossible or financially ruinous. Part 4. The economic solution. This brings us to the economics of safety. Let's look at the real example. Greenville Downtown Airport. They had a steep drop-off at the end of their runway. To build a traditional 1,000-foot safety area, they would have to build a massive earth embankment. The estimated cost was $16 million. Instead, they installed an Immerse. Because the material stops planes so efficiently, you don't need 1,000 feet. You can do the same job in a much shorter distance. The cost of the Immerse? $1.8 million. Compare one more time. 1.8 to $16 million. It saved the airport $14 million. And it provides the exact same level of safety. Part 5. A history of safes. This is not theoretical. This technology has a proven record called tombstone technology. Solution born from past accidents, but now saving lives. Since the first successful safe of a Saab 340 at JFK Airport in 1999, Immerse has stopped dozens of aircraft. In Charleston, West Virginia, a CRJ-200 regional jet aborted its takeoff. The runway ended at a steep mountainside. The Immerse caught it just in time. In Tattleboro, a Gulfstream 4 was stopped before it could cross a busy highway. And of course, the events of September 2025. 2 jets, 2 wet runways, 2 potential tragedies, 0 fatalities. But Immerse is only the last resort. Ideally, we never want to use it. To understand how we keep planes on the runway, we have to look deeper. We need to look at the invisible battle happening between the tire and the pavement. And it all starts with a formula from NASA. Part 6. The physics of touchdown. The most dangerous enemy of a landing aircraft is not wind, and it is not pilot error. It is water. When a plane lands, it is not just rolling. It is fighting a hydrodynamic battle. If the water on the runway is deeper than just 3 millimeters, 0.1 inches, a phenomenon called dynamic hydroplaning begins.
The water builds up pressure in front of the moving tire. It forms a wedge that physically lifts the rubber off the concrete. In the 1960s, engineers at NASA's Langley Research Center, they found that the speed at which you lose control depends on only one variable. It doesn't matter how heavy the airplane is, it doesn't matter how skilled the pilot is. The only thing that matters is the tire pressure. They created a formula that is still the Bible of aviation safety. Vp equals 9 square root of P. Here, Vp is the hydroplaning speed in knots, and P is the tire pressure in psi. Let's look at the numbers. A commercial airliner like a Boeing 777 has very high tire pressure, around 200 psi. According to the formula, it will hydroplane at about 127 knots. That is fast, but it is usually below the landing speed, so the risk is manageable. Its tires are only inflated to 36 psi. The formula tells us it will lose control at just 54 knots. This means a small plane is actually more likely to hydroplane than a massive jet. Part 7. Reverted rubber, the steam seal. But there is a type of hydroplaning that is even scarier. It is called reverted rubber hydroplaning. This happens when a pilot locks the wheels on a wet runway. The friction generates insane heat. This heat boils the water trapped under the tire, turning it into a high-pressure stream. The steam gets so hot that it melts the rubber on the tire, rewetting it back to its raw, sticky, uncured state. The result is a disaster. The melted rubber forms a seal around the steam, creating a cushion. The aircraft is now literally riding on a pocket of superheated steam. Investigators know when this happens. They find telltale signs on the runway. White marks that look like the pavement has been steam cleaned, elongated patches of melted rubber. Part 8. Engineering the surface. Grooving. So how do engineers fight this? We cannot stop it from raining, so we change the ground itself. If you look closely at the major runway, you will see it is not smooth. This is called grooving. Engineers cut thousands of channels across the runway. The FAA has a very strict standard for this geometry. The grooves are 1/4 inch 6 mm deep. They are 1/4 inch 6 mm wide. And they are spaced exactly 1.5 inches 38 mm apart. These tiny channels give the water an escape route. It flows into the grooves and drains away, allowing the tire to grip the length, the high points between the cuts. This simple geometric pattern can increase friction on wet pavement by up to 300%. But maintaining this is a nightmare. Every time a heavy jet lands, the tires spin up from 0 to 140 knots in an instant. This abrasion rubs off about 1.5 to 2 pounds of rubber onto the runway. Over time, this rubber fills the grooves. If 40% of the grooves are blocked, the runway becomes dangerous. That is when maintenance crews come in with ultra-high pressure water blasters, shooting water at 40,000 psi to strip the rubber off without destroying the concrete. Part 9. The layer cake. Hidden structure. Now let's go deeper. Literally. Passengers think a runway is just a road, but a highway is designed for trucks. A runway has to survive a 300-ton machine slamming into it at 250 km per hour. If you sliced a runway in half, you would see it is a massive engineering layer cake, more than 2.5 meters thick. Look at the cross-section. At the very top you have the surface course. This is the asphalt or concrete we see. Below that is the base course, often made of cement-treated aggregate. Then the subbase, and finally the subgrade, the native soil. In major international airports, the top layer alone can be 22 inches, 56 centimeters, of solid Portland cement concrete. This is thicker than the walls of a military bunker. This structure is designed to distribute the massive points of load of a single wheel. If the layers were not there, the landing gear would punch through the pavement and sink into the dirt. Part 10. The evolution of design. For decades, engineers designed these layers using old charts and tables called the ACN-PCN system. It was based on empirical data from the 1950s. But modern aircraft gear is too complex for simple charts. In July 2020, the Aviation world switched to a new standard, ACR-PCR. This is a mechanic approach. Engineers now use computer simulations called layered elastic analysis. They model the runway as a multi-layered elastic system in a digital environment. They can predict exactly how the pavement will bend and rebound under every single wheel of an Airbus A380. Part 11. The chemistry of asphalt. Finally, even the asphalt itself is high-tech chemistry. It is not just tar and rocks. Engineers use a performance grading (PG) system to design the binder. In a hot climate like Dubai, they might use PG 7622. The 76 means the asphalt won't melt or rot until it reaches 76 degrees Celsius. To achieve this, they modify the bitumen with polymers like CBS. It is basically turns the road into a very stiff rubber band. In a cold climate like Alaska, they use PG 5234. The 34 means it stays flexible down to minus 34 degrees Celsius, so it won't crack in the winter. We built the ground to match the sky, but even the best pavement is useless if the pilot can't see where to land. That is where the engineering of light comes in. Part 12. Tombstone technology. There is a dark saying in aviation: regulations are written in blood. Engineers call this tombstone technology. It means that many of the safety features we see today were invented only after a specific disaster. Take the tragedy of American Airlines Flight 1420. In 1999, an MD-82 jet overran the runway in Little Rock, Arkansas. It didn't stop in the grass. It collided with a rigid steel walkway that supported the approach lights. The steel structure didn't break. Instead, it tore the aircraft apart. That accident forced a critical change in engineering. It is called fungibility. Today, strict FAA rules state that any object located in the runway safety area, whether it is a light pole, a sign, or a navigation antenna, must be fungible. This means it is engineered to be brittle. It is strong enough to stand up to a storm, but designed to snap, buckle, or yield instantly if an aircraft hits it. The object must die, so the passengers can leave. We see this pattern everywhere. After the collision of two Boeing 747s in Tenerife in 1977, airports were required to install ground radar (ASDE) to see through fog. After the crash of Singapore Airlines Flight 006 in 2000, where a pilot turned onto a closed runway by mistake, lighting standards changed. Now taxiway lights must be physically locked out so they never lead a pilot to a closed runway. Part 13. The language of light. But the best safety system is one that prevents the accident before it happens. This brings us to engineering of light. When a pilot approaches a runway, they don't just guess their altitude. They look for a box of 4 lights on the left side of the runway, the precision approach patch indicator. It looks simple, but the optics are incredibly precise. The system is calibrated to define a perfect 3-degree glide path. Each light unit projects a split beam. The top half is white and the bottom half is red. The transition between the two colors is razor sharp, less than 3 minutes of arc. This creates a simple code for the pilot. For white lights, you are too high, more than 3.5 degrees. For red lights, you are too low, less than 2.5 degrees. This is dangerous, you might hit terrain. Too red and too white, you are perfectly on the 3-degree path. Part 14. The runway is talking. Once the wheel touches the ground, the engineering shifts from guidance to distance. At night, a pilot cannot easily see how much pavement is left, so the runway talks to them using color codes mandated by the FAA. The centerline lights, the lights running down the middle of the runway, are not just white. When there are 3,000 feet remaining, the lights start alternating red and white. This is the first warning. In the final 1,000 feet, the center line turns solid red. This tells the pilot, "You are running out of space. Stop now." Even the edge of lights participate. In the last 2,000 feet, or half the runway length, the white edge lights turn yellow. This creates a visual caution zone for the pilots. Now I'm serious. Which part of this hidden engineering surprised you the most? Was it the soft concrete of Immerse, or the fact that NASA formulas control your landing? Write your thoughts below. I read every comment. If you learned something new today, hitting the like and subscribe button is the best way to support me. As a new channel, every subscriber truly counts and motivates me to create better stories. Click here to watch the next